All right, everyone. So in the second half of today's class, we really talked about a power series representation of a specific function. So we really tried to find how we could represent the following function, 1 over 1 minus x, in a power series, or an infinitely long polynomial. So a couple things of just where we're going to go with this part of class. The main idea here is we're going to use what we know about geometric series to actually help us find the power series for 1 over 1 minus x. Now, this is just going to be the method we use to find the specific power series for this function. The main recipe of how we can find power series representations for other functions we'll talk about next class. These will be known as Taylor series. All right, so after we find this power series for 1 over 1 minus x, the next thing we'll do is we'll integrate and differentiate it to find other power series of other functions, and we'll also use what I call the stenciling method to find power series of other functions that look similar to 1 over 1 minus x. All right, so the first things first, let's find this power series, remembering what we have from geometric series. And before we actually find this and dive back into geometric series, I'm going to give us the spoiler, just so we know where we're going now. The spoiler here is we're going to see in a couple minutes that when we look for the power series for the function 1 over 1 minus x, that this is actually going to be equal to the series from n equals 0 to infinity of x to the power n. So this is what we're going to find in a few more minutes. And if we just write out the first couple terms of the series, we can see that it actually has the following format. So the first question is, we really want to know why. Where does this thing actually indeed come from? So I'm going to circle this because that's going to be one of the power series that we're going to use very often over the next couple days in class. So let's go back into geometric series for a moment. So this takes us back a couple weeks in class, maybe about 3 weeks or so. And just remember, a geometric series was a series that has the following format from n equals 1 to infinity of some number a times another number r to the n minus first. And now when we think about geometric series, remember when r in absolute values is less than 1, these geometric series converge. And what's special about geometric series when they converge is when they converge, we know what they're equal to. So if this geometric series converges, we know it's actually equal to a over 1 minus r. So I'll just write the note, if convergent. So we basically have the sum on the left-hand side, this a over 1 minus r, is equal to this infinitely long summation of values if r is less than 1 in absolute values. So this is where we're actually going to start here. Okay. And the first move that we can really think about making is, well, we're going to do some math substitutions. So we're going to do the following. We're going to let a equal 1, and we're going to let r equal x. And so we're going to take what we had before, a over 1 minus r, and that geometric series on the right-hand side, and we're just going to substitute those two values into it. So wherever there is an a, I'm going to put a 1. Wherever there's an r, I'm going to put an x. So we have 1 times x to the n minus first. And now, of course, well, we have multiplying by just that number 1, which was previously a. Well, that number 1 we can just get rid of, since multiplying by 1 just leaves us the same thing. So we can really think about the series in the following manner. And now the series that we have looks very, very similar to the power series I said we we're going to get up above, except there's some small differences. Those small differences, of course, are the series we have down here starts at n equals 1, and the power in the exponential is an n minus, or is an n minus 1 instead of an n. So what we actually can do is re-index this to make sure that we get the power series at the very top of the page. So the left-hand side here stays the same. And now when we re-index, what this means is we're going to subtract 1 or start at one lower index at n equals 0 instead of n equals 1 on our sum. We'll still have the sum go to infinity. And what that means, though, is because we're starting now at n equals 0 as opposed to n equals 1, we actually take that power that was there before and we add 1 to it. So instead of n minus 1, we have just x to the n. And that is where this power series relationship comes from between the function 1 over 1 minus x and the power series from n equals 0 to infinity of x to the n. Okay. So again, this is the thing that we're after, was this relationship. Now, the other piece I just want to mention is when we derive this power series, this geometric series was only equal to this final sum of a over 1 minus r when the absolute value of r was less than 1. So what that means for this power series down here, this relationship, when we called r equals x, well, the only way that this relationship down here holds is this is only true if the absolute value of x is less than 1. And now with us, in terms of our interval of convergence information, what this actually means is we need values of x between -1 and 1, but not including the endpoints. So this is only true if these values of x are held in that way. So again, for this particular power series, the interval of convergence would be -1 to 1, but not including the endpoints. And that again is related to the fact that for a geometric series to converge, we needed r to be less than 1. So again, this is the first power series that we have of a function. The function 1 over 1 minus x is equal to that power series n equals 0 to infinity, x to the n. So the next thing we're going to do, as I mentioned before, we're going to generate other power series based off this power series we know. And one way to do that is doing calculus on these things like we did in previous classes. We can integrate these power series, we can differentiate them. So let's go ahead and do that now. So this part I'll just call generating power series from other power series. Okay, so in example number 1, let's take the power series that we have and integrate both sides. Okay. All right, so we're going to start off with what we know, which is now this function and power series relationship between 1 over 1 minus x and the series from n equals 0 to infinity of x to the n. And in this problem, we're going to integrate both sides. So right now, this statement that we have is true as long as the absolute value of x, or the x values we're putting into it, are all between -1 and 1. And what we can do now, since this is an equivalency, we have left-hand side equals right-hand side. We do the same mathematical operation to both sides, and we would maintain that equivalence. So let's go ahead and integrate both sides here. And the first thing we're going to do is focus in on the right-hand side. We'll leave the left-hand side for a little later. And now looking at this right-hand side, the idea is to bring that integral inside of that sum. So it passes right by the summation. And the integral is really, again, going to only affect the terms that have x dependence. And well, in this power series, or this infinite sum, the only thing inside of that is an x to the n. And now if you pay close attention here, this is x to some power, so we're going to use the antiderivative power rule. Which means in this case, when we integrate that x to the n, we will get x to the power of n plus 1 all over n plus 1. And now since this was also an indefinite integral, an integral without any bounds, we also need an integration constant so we can tack on a plus c. So again, integrating power series is pretty nice because we're just going to use the antiderivative power rule. The next thing we can do is turn our sights to, well, integrating this function on the left-hand side. And if we integrate this function on the left-hand side, I'm going to try using a u sub with u equals 1 minus x. Du is then just equal to minus dx, or in other words, we have du over minus 1 is equal to dx. So let's go ahead and substitute all of that in on the left side. So we have 1 over u, and then substituting in the du over minus 1 for dx, we have du over minus 1. And that minus 1 is just a constant, so we can pull it into the front of the integral. And well, looking at the antiderivative of that left-hand side, we get the natural log of the absolute value of u. So we have, on the left-hand side, minus the ln of u in absolute value. And we can go one step further here because, again, we start off with our variable x. So we go back in terms of the variable x from the variable u. So I'll just erase that u and pop in what we have for u in terms of x, which was 1 minus x. So in this particular problem, we just found a new power series that's related to the natural log. So we found a power series for the negative natural log of 1 minus x. Now, in terms of this exact problem, all I want you to see from this is that we can generate other power series by integrating power series and the functions that they're coming from. For this particular problem, don't worry about memorizing this exact power series. What's more important is knowing the power series for 1 over 1 minus x at this point. Okay. Next, let's take that same power series, 1 over 1 minus x, and let's differentiate it instead of integrating it. So again, we start off with what we know. We have the function 1 over 1 minus x. It's equal to that infinite sum in terms of the power series of n equals 0 to infinity of x to the n. And again, this is only true for x values that fall between minus 1 and 1, not including those endpoints. So in this problem, we're told we're going to differentiate this. And since, again, we have left-hand side equals right-hand side, we want to do the same mathematical operation to both sides to maintain that equivalence. So we will differentiate both sides with respect to the variable x. And once again, we're going to pay attention more to what happens on the right-hand side first, and then we'll come back and worry about the left. So looking at where this derivative is going to act on everything to the right of it. And well, the first things first, we're going to bring that derivative inside of that sum. And since that's a derivative with respect to x, what it really cares about are the variable x terms, the terms with x dependence, in other words. So where we want to take that derivative is really on that x to the n term. So if we take the derivative of that x to the n term, if we look at what that term is, it is x to the n, a variable raised to a power. So we get to use the differentiation power rule. So we'll bring the power down, we'll subtract 1 from that power. So we have n times x to the n minus first is that particular power series now. So we know what the right-hand side is in terms of the power series. Again, differentiating power series, we are just going to get to use the power rule. The left-hand side, we could do this a couple different ways. We could do quotient rule. We could rewrite this to do a chain rule operation. So I'm just going to do a small side calculation to figure out what this derivative is on the left-hand side. So here's the derivative of the left-hand side, just doing a small side calculation. We have our function 1 over 1 minus x. I'm going to rewrite this as 1 minus x to the minus first. Let's zoom in here so you can see better. And then I'm going to take the derivative, and instead of using quotient rule, I'm going to basically do a chain rule, power rule type combination on this term on the right. So the first thing, I'm going to bring that minus 1 power down. Then we do the quantity 1 minus x. We raise that to the minus 1, or minus 2. Next, we multiply by the derivative of what's inside. The derivative of what's inside is a minus 1. So in all, this derivative comes out to minus 1 times this minus 1. So we get a positive 1. And then we have the 1 minus x to the negative 2. So this becomes a positive 1 over the quantity 1 minus x squared. So in terms of this on the right-hand side, this derivative on the right-hand side is a 1 over the quantity 1 minus x, that whole thing squared. So we just found another power series of a different function. In this case, the function 1 over 1 minus x quantity squared. And as we said before, I don't want you to memorize this specific power series down here. What's more important is knowing that, hey, taking a power series and a function that we know are related to each other, we can integrate those, differentiate those to find power series of other functions. The next thing we're going to do is, well, how can we find power series for functions that look similar? This is what I call stenciling. So to motivate this, I'm going to put this example on the right-hand side. Find a power series for, let's say, the function 1 over 1 minus x squared, instead of just 1 over 1 minus x. Let's look at 1 over 1 minus x squared. Now what we know is what I'm going to put on the left side. Right now we know we have the relationship 1 over 1 minus x is equal to the power series n equals 0 to infinity of x to the n when x is less than 1 in absolute value. Okay. So what I'm about to do is what I mean by stenciling. This stenciling technique will work whenever we have a power series and function relationship, as in we have a function and we know its power series. I'm just going to rewrite what we have, the same thing down below. And the next step I'm going to do is basically anywhere I see an x on the left side and x on the right side, I'm just going to go ahead and surround it with parentheses. Next, inside of those parentheses, I'm going to get rid of those x's. The reason for this, the idea being, well, whatever I put inside the parentheses there in the function side, I'm going to put over in the parentheses on the right-hand side as well. So this is what I mean by a stencil. We're going to first do this for the power series example that I motivated this with, the function 1 over 1 minus x squared. So to take that, we'll take this function 1 over 1 minus x squared, and well, what we see is, in terms of getting it into the stenciling form, we really just need to kind of put the x squared inside of those parentheses. And then we have on the right-hand side, those parentheses raised to the power of n. So what we can put inside of these parentheses is basically, well, the x squared, and then the x squared on the right-hand side as well. Just going to shift this over. And well, that is a power series for 1 over 1 minus x squared. It's the series from n equals 0 to infinity of x squared raised to the power of n. And now since we have powers raised to powers, we could rewrite the right-hand side, or that power series, from the series n equals 0 to infinity of just x to the 2n. Okay. So let's do another example here. Find a power series for, well, let's do 1 over 1 plus x squared this time, and then let's also integrate it. So the first part, we're looking for a power series for 1 over 1 plus x squared. Now this looks awfully similar to the last problem, except there's one big difference. We have a plus sign in the denominator, whereas previously we had only negative signs. So our goal is to take the function that we're starting with, or given in the problem, 1 over 1 plus x squared, and we want to try and get it into the form of that stencil. So we can just say whatever's in those parentheses on the left, we put in the parentheses over on the right. So to do this, the numerator will keep as 1. The denominator, we can just do one small mathematical sleight of hand. To generate that plus sign, we could do a minus x squared. And what that means is, well, we can wrap that minus x squared in parentheses. And now we have something that's in the form of our stencil, a 1 over 1 minus something. In this case, we have 1 over a 1 minus something, that something being a negative x squared. So we can pop that over into our power series on the right side. Again, do that stencil, wherever there was those parentheses, we raise whatever in those parentheses to the power of n, but whatever is on the left side parentheses, we'll put that over in the right side parenthesis. So this becomes a minus x squared, that whole quantity raised to the nth power. And now one last step we can do is we could simplify this a bit more. And this simplification will help us out as we go ahead and integrate this in a moment, because remember, the second part of the problem was just to integrate this. So inside of these parentheses, we have a negative 1 times an x squared, that whole thing raised to the power of n. So we could write this as the product of two terms, each being raised to the power of n. We can write this as a minus 1 to the n, and we can write this as a x to the 2n. So that was part 1. Finding a power series for 1 over 1 plus x squared. Next, in part 2, we were asked, well, once we find that power series, let's integrate it. So we have 1 over 1 plus x squared on the left. On the right-hand side, we have the power series we just found, n equals 0 to infinity, minus 1 to the n, times x to the 2n. And again, in this problem, we were told to integrate it, so that's what we're going to do. So let's go ahead and integrate both sides here. And again, we're going to start off with the right-hand side and do that integration of the power series first. So we bring that integral sign into the series, okay? It's going to ignore this minus 1 to the n, because that minus 1 to the n does not depend on x, so it's going to pass on by. So this looks like, oops, that's a 2n. So it looks like that following series to evaluate. Series n equals 1 to infinity minus 1 to the n times the integral of x to the 2n dx. And now again, this is a power series. The x is just raised to some power. We can use the antiderivative power rule. So when we integrate this, we'll have the series from n equals 0 to infinity minus 1 to the n. We will bump up that power by 1, so we'll get 2n plus 1, and we'll divide by that power plus 1 as well. Divide by 2n plus 1. And because this is an indefinite integral, we tack on a plus c. Okay, so we integrated the power series in this case. The next thing we can do is integrate this function on the left-hand side. And well, we've seen this function come up before and asking what its antiderivative is. You might recognize this from a couple of weeks ago when we talked about it, but this is actually the antiderivative for that, 1 over 1 plus x squared, is actually the inverse tangent function, or arctangent. If you don't remember, you can flip back to our notes. You can find the antiderivative with trig sub. And my point being in this case, that function on the left-hand side, like we saw before earlier in the semester, if we were to find the antiderivative of 1 over 1 plus x squared, we'd get to dive into a trig sub problem. Whereas if we knew what like in this case, we know what the power series representation is for 1 over 1 plus x squared, we can integrate that power series a whole lot easier than diving into that trig sub to actually get out that arctangent relationship here. Now, the last thing that I did in class today was just as something fun, as a fun side note, we can figure out some various aspects of arctangent and this power series relationship. So just to remind ourselves, what the arctangent gives us the angle whose tangent value is x. So the arctan of x gives us the angle whose arctangent value is equal to x, the x inside of that argument of arctangent. So what we're about to do is we're going to let x equal 1 in this case. So I'm just going to plug in 1 into both sides of this arctangent equation. So everywhere there's an x, just plugging in a 1. Right. Now, if we simplify the right-hand side, well, the only simplification we can do is 1 to any integer power is always going to be equal to 1. So we can rewrite that right-hand side as the power series n equals 0 to infinity of minus 1 all over 2n plus 1. And well, you might be wondering where I'm going with this. Well, you might remember an angle whose tangent value is equal to 1. That angle is equal to pi over 4. Since sine of pi over 4 and cosine of pi over 4 have the same value, that's where you can see sort of that relationship with tangent. Sine over cosine would give us a tangent value of 1 in this case for pi over 4. And if you multiply both sides by 4, you can get that pi is equal to 4 times the series from n equals 0 to infinity of minus 1 to the n all over 2n plus 1. So here's an infinite series representation of the number pi. And if you feel like it, you could evaluate this series for 10 terms, 100 terms, 1,000 terms, 10,000 terms, and just see how close and closer you get to pi, or how this actually converges to pi if you include all infinite terms. So that's what we covered in the second half of class. I will see you all in office hours or in class on Friday.